All right, today we'll continue writing our multi-threaded pool allocator in C. Let's first have a look at what we did last time. We created a simple struct that holds the internal state for our pool allocator. That's this one. And at the moment, our allocator can only handle objects of one specific type, which is the struct entity. Basically, for now, we've specialized our allocator for this type. We have this array of entities, which is kind of the backing storage of our allocator. That's the space that we're allocating from when the user calls alloc. The user is just going to get kind of a pointer to one of these objects. And when I say object, I don't mean object in the OOP sense. I just mean he's getting a memory location, a struct, a pointer to a struct. We have our free indices array. And that's the list of indices into our entities array that are still available to be allocated. And we have a pointer to the top of that stack. So if we just kind of illustrate what that means, let's say these are our entities, entity 1 to 4. And we start off with our indices array at 0, 1, 2, 3. And free top, the stack pointer, is going to point to the fourth element in the indices array, which is index 3. And now when the user calls alloc, which is the function down here, we first check if our stack top index, free top, is greater or equal to 0. And if it is, that means we have objects left for allocation. And in that case, we decrement our stack pointer, which means it moves from the fourth element to the third element. And we return a pointer to entity 4, to the caller of the alloc function. And just like that, we've made an allocation for the user of this entity. And now the next time someone calls alloc, we're going to decrement it again, move the pointer to the second element, and now we return a pointer to E3. Once we've allocated all of our available memory locations, our stack pointer is going to be at -1. And in that case, we aren't able to go into this if condition, and we just return null from our alloc function. And that's a valid return value of this alloc function. If we don't have any more space, we just return null. Now, for our dalloc function, we basically do kind of the reverse of that. We just increment our index pointer by 1. And then let me just close the window. We write the index of the object that is going to be deallocated into this slot of our index array. And that means that the entity at that index is now no longer available. Which means that, for example, if we allocate 3 to 1, 0, but then dealloc in some kind of different order, our index array might be, let's say, 2, 1, 3, 0. And the index pointer is going to be here, which means if someone now allocates another object, we return a pointer to entity at index 0, which is going to be E1. So the order of entities in our backing storage doesn't have anything to do with the order of indices in our index array. These are only in the same order in the beginning when we initialize those arrays. But after you've done allocations and deallocations in arbitrary ordering, those can be different. We also added a mutex to our allocator struct. And we use that mutex in our alloc and dealloc function. We call alloc at the beginning and unlock at the end. And we use this mutex to protect the internal state of our allocator so that if multiple threads call the pool alloc function at the same time without any synchronization on the call side, we are able to handle that internally and keep our data integrity. Yeah, and the same is true for the alloc, lock, and unlock. We also wrote a simple single-threaded test function for our allocator that just allocates for objects, asserts that on the fifth allocation, not on the fifth, whatever's object count 16. So on allocation 17, we should return null from our allocator when we're just asserting for that. We then deallocate all of these objects in kind of the reverse order. And then we're just checking if the free index array is in the order that we are expecting, which is this 3, 2, 1, 0, and it starts at 0, 1, 2, 3. We've reversed the order. This is just to make sure that our alloc and dealloc functions are not totally obviously broken. What we've then done is we also wanted to test if our allocator still works in a multi-threaded scenario. So we've just created a bunch of threads, and we started those threads with thread func as their execution function, which is calling alloc. And then we're waiting for that execution to end. And we've run all of that with, let me just show that as well, the Clang thread sanitizer to make sure that, or to get a bit more confident that we don't have any obvious issues. Now, with all of this, there might still be issues in here. We should definitely run this with address sanitizer as well. But for now, we have at least a bit of confidence that we're not totally wrong in our implementation. Now, what I would like to do today, let me just delete this. I would like to make our allocator generic in the sense that I no longer want to just be able to allocate struct entities, but I would like to introduce something like an object size that is being passed to the allocator during initialization. And then the objects that we allocate are of that specified size. Which means that, first of all, we're no longer able to allocate our backing storage kind of statically as we do right now. Like right now, we just have an inline array in our allocator struct that's our backing storage. We can't do that anymore because at compile time, we don't know what object size the caller is going to request. So what we will have instead is we will have a void pointer to, I'm just going to call it memory, which is our backing memory. For now, we can keep our index array and our stack pointer into that index array, and we can keep the mutex as well. But we do have to change our bool init function to now accept an object size. And I think I'm just going to make this size t of object size. And now we need to allocate that memory. And for now, I'm just going to use malloc for that purpose. So we do pool memory and set that to malloc object. Now, before we switch to make this generic, we used object count as the number of objects that our allocator can hand out. And for now, we're just going to keep that this way. Another thing that I want to do today is I want to change that to also be dynamic. So in addition to the object size, the caller would also pass an object count. But I'm not going to do that for now. For now, we're just going to keep our constant object count. So our allocated size for the backend memory is object count times object size. And I think that should be fine for this. Again, we don't do anything special with the memory that we allocated. We're not going to zero it. Just like malloc, we're going to assume that the caller does the appropriate initialization on the memory that they allocate. But now our alloc function has to change as well. Again, we no longer have the struct entity. We'll have a void pointer here. And same thing for the return type of the function. It's just going to be a void pointer. We still have to check if our stack top, free top is greater or equal to 0. If it's -1, we still have the case that the allocator has run out of memory. And now we need to set the result pointer to the pointer to the allocated object. And the way we do that is we have to take the base pointer of our backing memory, which is pool memory. And we need to add to that an offset of index times object size, number of bytes. To do that, we will convert our base, like our backing memory pointer, to a character pointer, because the character is defined to be 1 byte in size. And if we want to increment that pointer by some number of bytes, we have to cast to character pointer and do pointer arithmetic on that. So here we do pool memory, and we're going to add to that index times pool object size. Now, I think I actually didn't save the object size in here, which we need to do. So in addition to our backing memory, we now also have an object size variable in here. And after allocating the backing memory, we will set object size to the object size that has been passed in by the caller. And now we should be fine. So let's say when we initialize our pool, the user passed in an object size of 16. And let's also assume that our pool memory is at address 0, which is impossible on this platform, but let's just make it easier for us. So if we have index 3, for example, we're going to increment this base pointer by 3 times object size, which is 3 times 16, 48. That's the value that we are going to return at this point. Okay. The mutex is going to stay the same. We don't need to change any of that. But we do need to change our dalloc function. Our dalloc function now also has to take a void pointer to the allocated object that we're trying to deallocate. And the change here is going to be very simple. Right now, we get the index of the deallocated object by taking the pointer to it, subtracting from that the pointer or the base pointer to our backing memory, and dividing that by the size of right now the entities and now the specified object size. And everything else should still be fine, except we need to change this from the static entity array to our new generic backing memory. And we need to change the name of that to object. Now let's just check really quick that we've done everything correctly. Allocating backing memory, saving the size. This can stay the same. Parentheses, we get the index of our index stack. Increment the base pointer by index times object size. And on deallocation, we just do kind of the inverse, put the index back on the index stack, and return. So now in theory, that should be fine. So let's change our single-threaded test function first. Now in pool init, we now need to pass in the size of the object that we are trying to allocate. And for now, we're just going to reuse our entity struct in this case. We still have this array of entity pointers. This is just part of the test function. Our alloc function doesn't take any other arguments now. We're still going to return null if we've run out of space. And we're still passing the pointer to the dalloc function. The fact that our dalloc function now accepts a void pointer and we're giving it a struct entity pointer is fine. And this should also still work. Now for now, I think let's just run the single-threaded version first. Just to make sure that this works. Error to undeclared library function malloc. Yep, malloc is part of std_lib. And that seems to still work, which is great. So now let's incorporate our multi-threaded test again. And let's check that this also still works. We're creating threads. They're running the function. We're just allocating one object each and then waiting for the execution to finish. That should still work. And in this case, we also need to pass it the size. And it works. All right. So now we have changed our pool allocator to be able to allocate objects of an arbitrary user-defined size. Now, another feature that I would like to add to our allocator is to be able to handle running out of space and allocating more backing memory. So instead of just having a void pointer to a memory location, we would basically have some kind of array of kind of batches of objects. And we could, for example, allocate one batch during initialization. And then once we've run out of space on that batch, we would allocate backing memory for a second batch and then allocate objects from that batch until we've run out of space on that, allocate another batch, and so on. And with that, we can basically have an infinite number of, well, it's still, of course, limited by the memory that your operating system can provide. But simplistically, we have more backing memory able to be allocated. And the way I would like to do that, I think it's simpler if we just create kind of a fixed size array of batches first. So let's just make this an array of batch count. And let's set batch count to 4 for now. And for now, we're just going to set the first element. And we need another variable in here that kind of keeps track of which batch we are currently using. So I think I'm going to create another variable in here that's batch last, maybe. And this batch last variable is just going to keep track of how many batches we have allocated, which means that maybe I should call this batch count max and call this batch count. I think batch last is kind of a bad name for this. Let's set the batch count to 1. Yeah, I think this is better. For object count and thread count, it kind of does make sense to just call them count, because that is the actual number of those things that we have. But for batch count, this is really the maximum number of batches that our allocator can have. But we start off with just one batch. So we're gonna call it batch count max and batch count. So we need to now change our allocate function. And we basically will handle this case, which is we've run out of backing memory and we need to allocate another batch to be able to fulfill the request of the user. So we will create an else clause in here. And in this case, we need to first check if we actually have enough space to allocate one more batch. So we need to check if batch count is strictly less than batch count max. And if it is, we are incrementing batch count. And we will call malloc to allocate one extra batch. And we're going to save the pointer to that in to memory at the index batch count. So for the first expansion, for the second batch that we're going to allocate, the first one is allocated during initialization of our allocator. Batch count is going to be incremented to 2, which means we actually need to, the way we can do this is we can just call batch count increment after we set the value. So this is going to be 1. We set the batch pointer at index 1, second element, and then increment it by 1. And again, we're just going to allocate object count, just like we've done during initialization, times object size. And now we actually see a bit of a problem, which is that what actually happens to our indices array? Right now we just use like a linear index from 0 to object count that keeps track of the free elements in our entities array. But now we have multiple batches, which means we actually have several batches that can have an entity at index 0. So the way we can do that, I think the easiest way to do that is to just kind of increment our stack beyond object size, which is the size of one batch. And to get the index within one batch, we're going to do index modulo the size of each batch. And to get the index of the batch, we do index divided by the number of objects per batch. Let me just illustrate what I exactly mean by that. So let's say object count, which is the number of elements per batch, is 16. And the index is, let's say, 17. To get the index in batch, we just do index modulo object count. And that's going to give us 1 in this case. And to get the batch index, we do index divided by object count, which in this case is actually also 1. Maybe this is a bad example. Let me set this to 20. In this case, the remainder operation returns 4, and this still returns 1. 20 divided by 16, we're doing an integer division, so the batch index is 1. Which means if we just kind of illustrate our batches, we will have batch 1, entity 1, batch 1, entity 2, batch 1, entity 3, batch 1, entity 4. This is our first batch. And the same thing for our second batch. And our indices array is now just going to be 0, 1, 2, 3, 4, 5, 6, 7. And when we return index 7, we're going to calculate the index in batch like this and the batch index like this. And we will return a pointer to batch 2, entity 4, to the caller of the alloc function. So I think this is kind of the simplest way to handle this situation. Now, we've allocated more backing memory with our second batch, but we also need to kind of put more free indices on our index array. But now with that, we kind of see the second problem, which is that our free indices array also has a static size, which means when we allocate more batches, we kind of also need to make this array bigger, which we can't. It's a static array or statically sized array. So now we kind of have to think about if there's a better way to keep track of free elements that are still able to be allocated. And maybe let's just try to think about our options here. Now, the first option is kind of to just follow what we did for our backing memory, which is to kind of have batches of indices as well. And now each batch of objects also has an associated batch of indices. But this to me doesn't feel that great. We now have to like keep track and organize two different locations and make sure that whenever we allocate backing memory, we also allocate enough space for indices. When we deallocate a batch, we need to deallocate the associated index array as well. That to me doesn't feel like a great solution. And I think what's a better solution is to put the free indices kind of into the same memory location as the objects that we're allocating. Kind of to not have two separate things, but to make the list of free elements one with the objects that we're allocating. And I haven't fully planned this through, but kind of the first idea I have how to do this is to have basically a header for the objects that we're allocating. And this header would simply include a pointer to the next element in the list of free objects that are still able to be allocated. Let me try to actually kind of illustrate what I mean by that. Let's say I have entity one. This is kind of the first element that is able to be allocated. It would have a pointer to, maybe let's draw a pointer symbol like this, to entity 2. And entity 2 would have a pointer to entity 3. And let's say we just have 3 objects that are free for allocation. E3 could have kind of a null pointer to signal that there's no object that it's connected to. There's no next object that is available for allocation. This is the end of the list. And when we now allocate an entity or an object in the new generic world, we remove, in this case, E1 from the list. And now we have E2 as our first element in the list. E2 would still point to E3 as the next element in the list. and E3 would still point to null to signal the end of the list. And now we've removed E1, and E1 would now be able to be used by the caller of our alloc function. And to keep track of the first element in our list of objects that are available for allocation, we would just keep that index or pointer to that object in our pool data, which means our pool could have some kind of maybe next, or just available. Available should be fine. So if we go back to this example, available would first be set to E1. Then we allocate E1, which is removing it from the list, and then setting our available pointer in the pool struct to E2. So now the next time we call alloc, we would remove E2 from this list, set available down here to E3, return E2 to the caller, and the next time we alloc, we now allocate E3, and so on. Now, once we've gone through all the available elements, available would just be set to null, which in theory should just use the same logic that we've used before. We're just setting it to whatever the value of the next pointer in the entity is, taking that value and setting available to that. And this would kind of be, I think, a simpler way, even simpler than what we have right now, to handle the list of allocatable objects. So let's just implement this and try if this works. So for now, I think it is easier if we just expect the caller to have our header struct as the first element in their specified object. So let's just define a struct header, and this header is just going to have one pointer inside of it, which is just the next available element in the list of free objects. And for now, we're just going to have this header as the first element in our entity struct. Now, the reason why it needs to be the first element is our allocator doesn't have any knowledge of, in this case, the entity struct. It just knows that the object that the user is trying to allocate is of a certain size. That's the object size that is passed during initialization. But it doesn't have any knowledge of what that object is. But if we specify our header as the first element inside the struct, or if we make that part of our API, we just expect the user to have this header as the first element in the struct, we can cast a pointer to an entity or a generic pointer to a struct header pointer, meaning every struct entity pointer is also a valid struct header pointer. And that's kind of how we will save data in an object that is defined by the user without having any kind of knowledge about that object. Now, I think ideally we wouldn't want that to be part of our API. It's almost like dangerous to have the user adhere to some API like this. Like you have to define struct header as the first element of your struct. That's it's kind of a dangerous thing to do. The user mightn't put it as the first element, which would be wrong. They might not put it in there at all, which means we override kind of parts of their struct. They're even worse. They might actually have a struct that is smaller than our header struct. So, for example, if I have a UN32 down here, no header, now the struct entity size is smaller than the size of struct header, which means that if we write some value to next available, we're actually overriding, in this case where we have 8-byte pointers, we're actually going to override the internal data of two entities by writing to our pointer. This is why it's a bit dangerous. But I think for now we just control everything, and this makes it a bit easier for us. So for now we just add our health attribute, which is just some example, and add the header. And I think to make this consistent, I'm also going to call this next available. So now with this change, we actually don't need a pointer to the first, like to the topmost element on our free stack. We don't have a free stack anymore. The pointer to free elements are now just part of our allocated object, which means we can remove our free top variable. We're going to keep object size, and this should be fine. Now with this change, we also need to change this part right here, which is where we initialize our free indices array. And we have to change that to now kind of initialize our chain of next available elements. So instead of setting free indices, we now set pool memory. This is the base pointer to that batch of objects. And we're going to do the same thing that we do for allocation, where we cast it to a character pointer. And to access the element at index I, we're just going to do the same thing that we did before, where we multiply the index with the object size. And this is how we increment the pointer to be a certain byte offset away from the start of the memory region. And we're going to cast the result of this operation to a struct header pointer. So now with this operation, we have a pointer to each header of all the objects in our batch. And now we just need to initialize the next available pointer to the correct value. And I think if I just try to illustrate again what the correct value would be. If we have these 4 entities, we want E4, in this case, for example, to point to E3. we want E3 to point to E2, E2 to E1, and E1 to null. And just like that, we've kind of defined a chain of entities that are available for allocation. They each point to the element kind of one index below them in the backing memory array. So let's just implement that right here. Now, since the first entity needs special handling, I'm actually going to begin at index 1. And index 1, or the header at index 1, next available, is going to be set to header -1. This looks a bit weird, but this is just pointer arithmetic in C, where actually this is wrong. But interesting. So let's talk about that. I have a pointer to the header of each object. And -1, doing pointer arithmetic in that way, means that from our header pointer, we subtract size of header. But size of header is smaller than the size of the entity, which means that if we subtract 1 like I did down here, we will now not land at the header of the previous element. We're going to land somewhere in the middle of that entity, which is obviously wrong. What we actually need to do is let's create a kind of a second variable here and call that previous header. And instead of using I as the index, we now use I -1. And this is the correct way to do this. So now we set the next available pointer of header to the pointer of the previous header. And actually, in this case, we don't even need a pointer to the header. We can just make this a void pointer, just call it previous, because the header and the object itself, they start at the same address. This is what I explained earlier. And our next available pointer isn't strictly a pointer to the header. It's just a pointer to the previous element. So we don't need this. And we just create a pointer that is I -1 times object size offset from the base address of our backing memory. And now let's set this pointer to previous. We can now delete the free indices assignment and also the free top assignment that doesn't exist anymore. Now in here we have two things left to do. We need to set the first element. So we're going to cast the base pointer of our backing memory to struct header, just as we did before. And we're going to set its next available pointer to null. And this is kind of how we signal the end of the list, as I explained earlier. So now the last thing to do is to set the next available pointer of our allocator to the head of our list, which in this case is just going to be the last element in this first allocated batch of elements. So pool next available is just going to be the pointer to our backing memory incremented by object count -1. This gives us the last element without going like past the memory region that we allocated, times object size. And I think this should be fine. So now we also need to change our pool alloc function. We now no longer check if our stack pointer is greater or equal to 0, because we don't have a stack pointer anymore. We now check if our next available pointer in our allocator struct points to a valid object, or if it points to null. If it points to null, we either allocate more backing storage, or if we've already exhausted all of our batches, we then still return null from our alloc function. So let's implement that check. If pool next available is not equal to null, and in that case, we return pool next available. But since we don't return from here because we still have our mutex, we actually need to set result to pool next available. And we then obviously need to change our next available pointer to point to the next element in our list of free objects, which means we're going to look at the next available pointer of the object, read that value, and write it to the allocator's next available pointer. So let's do that right here. Pool's next available pointer is set to, and now we need to read that value from the object, which means we cast the pointer to the next available object to get to its header. And we now get its next available pointer. So we basically, I think it does actually make sense to illustrate this again. We have our entity 1. Actually, we have our entity 2. Let's do it this way. And its next available pointer points to E1. And then we have E1, and its next available pointer points to null. And actually, let's even add a third entity here and set its next available pointer to E2. This is kind of the way we initialized our allocator. It's always set to the last or to the previous element in the backing memory array. And remember, these values are only sorted right after initialization. As soon as the user of our allocator allocates and deallocates objects in some user-defined order, our entities will no longer be like in strictly incrementing or decrementing ordering. But let's go through this. So let's also kind of illustrate our pool. Its next available pointer at the beginning points to E3. So now in this case, we would set the result pointer to the pool's next available pointer, which is a pointer to entity 3. And then we take this pointer, pool next available pointer, we cast it to a struct header pointer, which means we interpret the first bytes at the memory region of E3, and we just like read the bytes of the header by casting it to a header pointer and reading its value. And we dereference the next available value, which in this case, E3's next available value is a pointer to E2. So now the pool's next available pointer is going to change to a pointer to entity 2. And this entity is now no longer of our list of 3 elements. It's now, we've kind of transferred ownership of this value to the caller of our alloc function. And now the next time someone calls pool alloc, we will return a pointer to E2, because that's what our pool's next available pointer is set to. We're going to set this value to E1, transfer ownership to this object, and so on, until we've reached the point where we read next available from E1, which is null, set our pool's next available pointer to null, and at that point we've completely exhausted our list of available elements and either allocate more backing memory or return null from our alloc function. And that's actually exactly the case that we can handle next. So that is the case right here. If the pool next available value is equal to null, we need to handle that by either allocating more storage using, for example, malloc, as we do right now, or by returning null from our function. And which of these two we do depends on how many batches we currently have. If batch count is equal to batch count max, that means that we have already allocated all the batches that we are allowed to allocate according to the definition of batch count max. But if batch count is less than batch count max, we are going to allocate a new batch and return the first element of that new batch. So let's do that. Now, we need to check if pool batch count is strictly less than batch count max. And if that's the case, we allocate one more batch, which means we will set the pointer at pool batch count to the result of malloc. of object count, which is again the number of objects per batch, times the object size that the user specified during initialization. But just allocating more memory isn't enough. We need to do the same thing that we did during initialization of the allocator, where we also initialize the headers of our allocated objects. We kind of need to rebuild this chain of free objects. So let's do that as well. We're going to do a simple for loop again over all the objects of this batch. We're going to effectively just do the same thing that we did right here. And now, for now, I'm just going to copy the code that we have right here. But we're starting to see that we've kind of duplicated logic in our initialization and in this case of the alloc function. And if we think about it, we could handle this in kind of a unified way very simply by simply setting our batch count to 0 at the beginning and setting the pool next available pointer to null during initialization, which means that we fall into this case right from the beginning. And I'm going to finish this first, but this is kind of the next thing that we can do. So I'm just going to copy this code. And initialize our backend memory. Now, the only change that we need to make, during initialization, we assumed that we initialize batch at index 0, batch 1. But what we actually need to do is we need to take the pointer at the newly allocated batch index, which is going to be pool batch count. So let's just go like mentally through this logic right here and see if it's actually correct. Let's try to do this for the second batch, so batch at index 1. In this case, we would start with a batch count of 1. 1 would be strictly less than 4, which means that we go into this if condition. We set the memory pointer at index 1 to the result of malloc. This looks good. And then we initialize all the objects inside this newly allocated batch. And we do this by taking the base pointer to this batch of objects, pool memory at index 1 in this example, increment that by I times object size. This is going to give us the offset pointer to the element at index I. We're going to cast that to its first member, which is the header, and cast the pointer to struct header. This was correct. And we set its header next available value to the previous value. And the mistake we've made here is we've not given it the same treatment as before, which is taking the batch at index batch count, increment that by I minus 1, because we want the previous element times object size. And that's going to give us the previous value. And this looks good. We also need to initialize the first value in our backing memory, which is this line again. We cast the first element of our batch to its header and set the next available pointer to null. Yeah, this looks good. And finally, we need to set the pool's next available pointer to the last element in our newly allocated batch. So again, we need to do pool batch count down here. I actually forgot pool before this. Offset the pointer by object count minus 1, which gives us the last element of this array multiplied by object size to get the byte offset. And I think this looks good. So now, as I said earlier, we have this duplicated logic between this case and our initialization. And the simplest way to fix that is to just remove it from here, set the initial value of the pool's next available pointer to null, and to set the initial batch count to 0. So now when we go through this logic, we see that the pool next available pointer is going to be null in the first allocation, which means we land in this case. And batch count will be less than batch count max because batch count is 0 after initialization. And we set the pointer at index batch count, which is still 0, to the result of malloc. And we go through the exact same logic that we had before. So I think this looks good. So now we need to delete the logic that we had previously. I think none of this is needed. We don't have free top anymore. We don't have a stack of available objects. Batch count is less than batch count max. All of that is handled differently now. But one thing we haven't done yet is after we've allocated a new batch, we still need to set the result pointer because we are still in the alloc function and we need to return a pointer to some allocated object. So in this case, we would actually duplicate logic again because what we would have to do, our next available pointer is now the last element of our newly allocated batch. And this last value is also the value that we would return to the caller. So we would set result to pool next available, and then we would set pool next available to basically exactly the same thing that we have right here. We would read the last element's next available pointer, go to that header, and write its next available pointer to the pool's next available pointer. Now, since that is kind of weird to have the same logic duplicated, I think there's actually a better way to do this. by simply checking if next available is equal to null in the beginning. So we're just gonna duplicate this here. And if it is null, we execute the logic here to allocate a new batch. And then we simply use our existing logic to allocate an object. And let's go through this logic again. Next available, if it is null, we allocate a new batch. We set our pool's next available pointer to the last element in our new batch. And we don't set the result pointer yet, which means we can actually kind of put it down here. Which means our next available value in the pool is now a valid element. So now we can do this check. Pool next available is now going to be not null. We set result to that value. And we kind of take the next value in the chain. This is kind of exactly what we would like to happen. And if pool next available is null, which means we weren't able to allocate a new batch, then we're going to still return null from this alloc function. An alternative, what you might want to do kind of depends on your use case. If you actually want to know that you've run out of batches, because, for example, you set this as some like, compile time constant, you could have some kind of assert here that just shows you that you've run out of space. But I think I actually don't really want that. I kind of like the logic that running out of batches is the only case where our allocator returns null. I think this is a sensible API for this. So now we also need to change our dalloc function. And again, our dalloc function kind of needs to do the inverse of our alloc function. Which means if we have, for example, a free list that is E2, it has a pointer to E1, and it has a pointer to null. When we deallocate, we return an element to our free list, which means what we want to have after this operation is E3 having a pointer to E2, the current topmost element, and E2 is still having a pointer to E1, and E1 is still the end of the list. So let's try to implement that. Now, the first thing that we need to do is we need to get the pointer to the current top of the list, the last element of the list. And we're going to cast that to... Actually, we don't need to cast it to its pointer. All that we need to do is to set E3s, which is E3 is the deallocated object. We need to set its next available pointer to a pointer to E2, which means we cast our object to a struct header pointer. and set its next available pointer to the pool's next available pointer. And now we need to also refresh the next available pointer of our pool, so that the next time that we allocate something, we now take E3 as our allocated object. So pool next available is going to be set to object. And now we don't need to do our index calculation anymore, because we don't deal with indices, we just deal with the pointers to the elements directly. So I'm going to delete this. And let's make sure that this actually works for the case where next available is null as well. If the current top of the free list is equal to null, which means we don't have any objects available for allocation, our object's next available pointer is set to null. And we still set the pool next available pointer to object. And that's exactly what we want, which means after this deallocation, we will end up with E1 as at the top of our free list. And it's just going to have a pointer to null. And that looks good. That's kind of exactly what we want, because now when we allocate an object again, our pool's next available pointer is going to be set back to null. And we're going to return E1. So I think this looks good. And again, I kind of want to start with our single-threaded test, just kind of doing the easiest thing first. And we're probably going to get some compilation issues. Undeclared identifier object size on line 42. Yep, that totally makes sense. We need to use the object size that we saved in the pool struct. We've done the same thing here. And actually, we've done the same thing here as well. We don't have free indices in struct pool. That's on line 82. This is our test case, I guess. So for now, let's just kind of comment this out. And now we have an assertion failure. This actually makes sense, because the way our test case works currently, it assumes that we only have one batch, which means after we've allocated all the objects of the first batch, we would return null. But now, since we have the ability to create extra batches, in the case where we've run out of space on the existing batches, this assertion is actually wrong. So what we now need to do in our test case is we create all the batches that we can ever have, allocate all the objects of those batches, and then we check that the next time we try to allocate something, we return null. Actually, let me turn this into B. And for now, let's not save our entity pointers. Let's just allocate these objects and not do anything with them. So we're going to loop. Our batch count max was 4, so 4 times. Going to loop through all the objects, which means we're going to do batch count max times object count allocations, so 64 allocations. And after those 64 allocations, we should be in the case where we're no longer allowed to create more batches, and now our allocator should return null. For now, let's also comment out the dalloc test and run this. And our assertion still fails. So let's try to understand this. We've created a number of batches. Actually, let's try to understand this step by step. Let's first check that the pointer that we return from here is not null, meaning that we do actually allocate batches and we are actually able to allocate objects from our batches. And this seems to work. But it seems that we aren't able to return null after that. And I think I know what's wrong. We never increment our batch count, which means it's always set to null, sorry, to 0. Which means we always land in the case where batch count is strictly less than batch count max. And therefore we never return null from this function. So what we actually need to do as the last step down here is to increment batch count. Let's try if this makes things better. Yeah, this is good. So let's now also test our dalloc function. And for now, let's just deallocate all the objects again. So we do a pool dalloc. And actually now we need our entity pointer array again. And it now needs to be of size batch count max times object count. Struct entity, that's going to be the result of the alloc function. I still want to assert that it's not null, just to make sure that our logic here is correct, or that it's not completely wrong. Correctness is maybe a bit too much. And we're going to set entities at index b times object count plus I to this entity pointer. This assertion is still useful. We do actually want to make sure that it's null after we've run out of space. And now in the dalloc function, we simply return this entity back to our allocator. Dalloc, this is a pointer. And now we can just, to make sure that this works, assert that our alloc function now does actually return a valid entity again, because we've filled up our allocator again. We've returned our elements to the allocator. So now we should have objects available for allocation again. Let's make sure that this works. Yes. Actually don't want to check here. I do want to check here. Okay, this looks good. So as a last step, I think we can now make sure that our multi-threaded test case also still works. So we create our pool, we initialize it with the size of our struct entity. That's still good. We have our 4 threads. Create them, execute the thread function, and then wait for execution. We allocate from our pool. Let's just write an assertion here that the entity that we return is actually not null. And that should be okay. That looks good. Let's make sure that we also have thread sanitizer still enabled, and we do. Okay, I think I'm happy with that. We have extended our allocator to be able to handle objects of an arbitrary size defined by the user during initialization. And we have implemented behavior that makes it possible to allocate the backing memory in batches. I think this is pretty good. Now, what I want to do next is I think I want to write some kind of performance test for this mutex-based version of our allocator, just to have like some kind of baseline for the performance. Then I want to re-implement parts of the behavior that we have right now using atomics, and then kind of compare the performance between mutex and atomics. Now I know that this is not going to be some like general comparison between using mutexes in your code and using atomics, but I at least want to get a feel for how those two things behave in the context of a simple allocator like this one. But I think before we do that, I want to take a quick break and see you then.